Hello students, in our today's lecture we are going to see the examples solve the following congruences. Our first example is 7x congruent to 3 mod 12, 3x congruent to mod 125, that is here modulo is 125, 15x is congruent to 8 modulo 25 and 259x is congruent to 5 modulo 11. Okay, we see this example, how to solve this example. Before that, what we know, the number of solution, if the GCD of this, that is our general solution, general linear congruence is Ax congruent to B modulo M. Okay, and if the GCD of A comma M is equals to D and D divide B, then we have the solution of this congruence, right? That is when D divides this GCD of this divide the number B, then we say that this equation has a solution, and the number of solution will be exactly D in number. Okay, so number of solutions is equals to D. Okay, and which are incongruent solution. So we solve this first equation 7x congruent to 3 modulo 12 by two methods. Our first one is by solving the Diophantine equation, and second method we use the inverse modulo that we see in the last lecture. Okay, so let's see. In a solution we write here D, that is equals to the GCD of this 7 and 12. So GCD of 7 comma 12, what is it? This is equals to 1. Okay, so the GCD is equals to 1, hence the given equation has a unique solution. And its linear Diophantine equation, that is for this equation in general, the linear Diophantine equation of this is Ax minus by is equals to M. Sorry, it is Ax minus my is equals to b. Okay, so the Diophantine equation which is equivalent to this equation is our Ax minus my is equals to b. So we express this equation in this form, that is in a Diophantine equation form, as so the equivalent Diophantine equation of given equation is 7x minus 12y, which is equals to, because here A is our 7, B is equals to 3 and M is equals to 12. So substituting the value of A as 7, M as 12, and here B is equals to 3. Okay, so 7x minus 12y equal to 3. Now we can solve this Diophantine equation by the Euclidean algorithm, and here as the GCD of 7 comma 12 is given to be 1, so we can express the GCD in the form that if we have the GCD of A comma B is equals to D, then we express this in the form Ax plus by is equals to D. Okay, so we express in the same manner we express this 7x, that is we can express 7 and 12, the GCD of 7 and 12 equals to 1 in this form. Okay, so let's see, by the Euclidean algorithm we can write, we can express, because in 7 and 12 is bigger, so we write 12 is equals to, what is 12 is equals to, as we have to find the GCD of 7 comma 12 is equals to 1. Okay, so we express 7 and 12 as a linear combination, and this is equal to 1. Okay, so 7x plus 12y, we have to express this as equals to 1. So we find to find the GCD we apply the Euclidean algorithm, and which is given by, we take 12 and by division algorithm this can be expressed as 12 is equals to 7 into 1, 7 ones are 7, plus the remainder is 5. Okay, we divide this 12 by 7, so 12 is expressed as 7 into 1 plus 5. Now this 7 can be expressed as 5 into 1 plus 2. Okay, that is we multiply, that is 7, we divide this 7 by 5, so 7 is equals to 5 into 1, 5 ones are 5, and the remainder is 2. Now again the remainder is non-zero, therefore we divide this 5 by 2. So 5 is expressed as 2 into 2, and the remainder 2 to the is 4. So when 5 is divided by 2, so remainder is our 1. Now again the remainder is non-zero. Okay, so we divide this 2 by 1. So 2 can be, by a division algorithm, 2 is equals to 2 into 1 plus the remainder now is, it is 0. Okay, so we get here the last non-zero remainder is 1. Okay, and therefore this is the GCD of 7 and 12. And thus we can write this, the GCD of 7 and 12 as, we can express this one in the form of 7 and 12. So we write this one as 5 and we take 2 by 2 multiplied by 2 to this side. So we write 1 is equals to 5 minus this term, 2 into 2. Now that is equals to, now this 2 is our remainder. So 2 can be expressed as 7 minus 5 into 1. So 5 is as it is minus 2 multiplied by, we write this 2. From this 2 we can write this term as 7 minus 5 into 1. Okay. Now opening the bracket we have 5 minus 2 into 7 minus and minus plus 2 into 5. Okay, so adding this term we get 3 into 5 because 2 into 5 and this is 1 into 5. So 2 plus 1 is 3 into 5 minus 2 into 7. Now this 5 can be taken from this last equation because 5 is remainder. So we can write this 5 as 12 minus 7 into 1. Okay, so we write 3 multiplied by 5. 5 is our, from this equation it is 12 minus 7 into 1 minus 2 into 7. Okay, so it return as 3 into 12 minus 3 into 7 because 7 into 1 is 7. So 3 into 7 we write minus 2 into 7. So adding this 2 we get 3 into 12 minus 3 minus 2 is minus 5 into 7. And we can write this term as in the form of, we write this in the form 7x minus 12y. Okay, so 7x, so we write this 7 into minus 5 minus 12 into minus 3. Okay, that is this 7x minus 12y, but this is equals to 1 and we require that 7x minus 12y equals to 3 because the GCD is here is 1. So we multiply this equation by 3 and therefore we get 3 is equals to 7 into, we multiply 5 by 3, so minus 15, 5 3 is minus 15, minus 12 into minus 3 into 3 is minus 9. So it is minus 12 into minus 9 and which is equals to 3. Okay, therefore by comparing this with the equation, we give this as the equation number 1. So comparing this with equation 1, comparing this with the equation 1, we get x is equals to, that is x0. The first particular solution we get x0 is equals to minus 15. And therefore the solution of our equation, that is, we write here the solution of our equation, that is 7x, our congruent equation 7x congruent to 3 modulo 12 will be is equals to x is congruent to minus 15 which is congruent to 9 modulo 12. Okay, that is because here our first solution x0 is obtained here. Now from this solution we can write our first solution of the linear congruence is given by x is congruent to minus 15 which is congruent to, because here minus 15 is congruent to 9 under the modulo 12. This is because 12 to is 24. Okay, and 24 minus 15 is congruent to 9, right? So x is congruent to 9 modulo 12. Now we see the second method. This is we see the first method. Now we see the another method. Another method means we can solve in this way also by using the inverse modulo. So for the inverse modulo we write, we have 7x congruent to 3 modulo 7x is congruent to, given that it is 3 modulo 12. Okay. Now we have to find the inverse of 7 so that it can be written in this form. What the inverse modulo method is, we write firstly the method and then we solve. So see, if ax is congruent to b modulo m, in general if ax is congruent to this, then we have the solution that x is congruent to a bar into b modulo m if the GCD of a comma m is equals to 1. If the GCD of a comma m is equals to 1, then we can apply the inverse method. And what this inverse method is, then the solution x is congruent to a bar b modulo m. And how this inverse is find out? This inverse can be find by we can take the a into something multiplication. If we take a into y, which is congruent to 1 modulo m, that is we required some number. When we multiply this number by a by y, then this is congruent to 1 modulo m, then y is called as the inverse of a under this modulo m. Okay, so let's see. So now we solve the 7x congruent to modulo 12. So we write 7x is congruent to 1 modulo 12. Okay, that is we write firstly we find the inverse of 7. So for this we require 7 into x is congruent to 1 modulo 12. Okay, so 7x is congruent to 1 modulo 12. What this implies? X is congruent to 7 modulo 12, because since 7 into 7 is congruent to 7 7 is 49, which is congruent to 1 under modulo 12, because when we divide this 49 by 12, we get the remainder 1, because 12 4s is 48. Okay, so we get the remainder 1. So 7, the inverse of 7 is equals to 7 itself. Okay, so we have x is congruent to 7 modulo 12, and therefore what we taken here now? So what this implies? The inverse of 7 is 7 itself. Therefore we multiply the given congruence equation by 7. Okay, by 7, therefore we get 7x congruent to 3 modulo 12 implies that 7 into 7x is congruent to 7 into 3 modulo 12, and 7 into 7 is our 49, which is congruent to 1 under this modulo 12. Okay, so we get 1x is congruent to 7 3 is 21 modulo 12, and therefore we get that x is congruent to, what is 21? 21 under modulo 12 is our 9 under modulo 12, because when we divide this 21 by 12, we get the remainder 9. Okay, so we have x is congruent to 9 modulo 12. Okay, so in some cases we can apply the inverse modulo method, that is when the GCD, because since we can here apply the inverse modulo method, because the GCD of 7 comma 12 is given to be 1. Okay, what is the GCD? GCD is equals to 1. So in this case only we can apply the inverse modulo method. Now we see the second example B, which is given by 3x is congruent to 1 modulo 125. Okay, now here we use we can use some different method. So see, here we firstly what we have to find, firstly we have to find the number of solution, and for this we take the GCD of 3 and 125. So here in a solution we write here the GCD of 3 comma 125. What is the GCD of this? Because 125 is not divisible by 3. Also there are no common factors, so the GCD is equals to 1. And therefore we can say that what this implies, the given congruence relation, given congruence has unique solution. And this 1 is also divide this 1. Okay. Therefore this has a unique solution modulo what? Modulo is given to be 125. Modulo 125. Okay. Now we can write this congruence 3x is congruent to 1 modulo 125. This is our given equation. We also know that 125, that is 0, is congruent to 125 under modulo 125, because 125 is divisible by 125 and therefore 125 is congruent to 0 under the modulo 125, right? Now we can add this to equation. 3x plus 0 is congruent to 1 plus 125 is 126 with a modulo 125. Since A congruent to B modulo M and C congruent to D modulo M, then we have the addition can be possible, that is A plus C is congruent to B plus D modulo M, right? So here what we have make here, we have done here that we take the number 125 such that, because 125 is not divisible by 3, we can add some number in 125 such that is, when we add this 125 to 1, it becomes a 126, and 126 can be divisible by 3 because 6 plus 2 is 8, 8 plus 1 is 9. Okay, so this number is divisible by 3 and therefore we can write here, we can divide this equation by 3. So dividing by 3, we get x is congruent to, divide by 3, what 126 divisible by 3, we get 42. Okay, under modulo 125. Now this gives you, and since we can divide this equation, because again the GCD of 3 and 125 is 1. Okay, so division is possible only when the GCD is equals to 1. We cannot divide each and every time. Okay, so here we divide this by 3 because the GCD is equals to 1 and therefore x is congruent to 42 modulo 125, and here we get the solution. Okay, so this is a required solution. Now our equation C is our 15x is congruent to 8 modulo 25. 15x is congruent to 8 modulo 25. This is our example C. Now here the GCD of, what is the GCD of 15 and 25? It is, the common GCD is 5. Okay, the greatest common divisor which divide both the numbers is 5, and 5 does not divide 8 because 5. So here this equation has a solution when D divides B. Okay, but here 5 is not dividing 8. Also 5 is not dividing 8. What this implies, the given congruence, the given equation has no solution. Okay, so to check whether the given equation has a solution or not, what we have to check, we have to first find the GCD, and if this GCD is divide this B, then the number of solutions are exactly equals to D. But if it does not divide, then we have no solution for this given congruence. Okay, so our example C has no solution. Now we see the example D, that is 259x is congruent to 5 modulo 11. Now here the GCD of 259, 11, the GCD is equal to 1. Okay, now this number, also this, what this implies, then if the GCD is equals to 1, then this implies that the given congruence given equation has a unique solution. Okay, so given equation has a unique solution. Now we take, now our given equation is 259x is congruent to 5 modulo 11, and we know the number which is near to 259, that 253. This number is congruent to 0 mod 11 because the sum of 2 plus 3 is 5 and 5 minus 5 is 0. So we apply here the divisibility test for 11, and therefore this can be say that 253 is divisible by 11, and therefore we have the remainder 0. Okay, therefore we say that 253 is congruent to 0 modulo 11. Okay, so you can use the divisibility test to quickly know the given number is divisible by some number or not. Okay, so you can apply here the divisibility test of 11 to show that this number is divisible by 11 and therefore it is congruent to 0 mod 11. Okay, and this number is very near to 259, and therefore we can take the subtraction of these two equations. So by taking subtraction, we get that 259 minus 253 is 6x, which is congruent to 5 minus 0 is 5 modulo 11. Okay, so 6x is congruent to 5 mod 11, and the GCD of 6 and 11, GCD of 6 comma 11 is equals to 1. Therefore we can take here, we know that 5 is congruent to minus 6 modulo 11. Okay, we can write 5 which is congruent to minus 6 modulo 11. Therefore we can combine these two, that is 6x is congruent to 5 mod 11 and 5 is congruent to minus 6 mod 11. Both will implies that 6x is congruent to minus 6 mod 11 because of the property of transitivity. Okay, that is when A is congruent to B mod M and B is congruent to C modulo M, then what this implies that A is congruent to C modulo M. So here we apply this to these two equations, that 6x is congruent to 5 mod 11 and 5 is congruent to minus 6 mod 11. Both these two implies that 6x is congruent to minus 6 mod 11. Therefore what we get, therefore as we can divide here by 6, therefore x is congruent to minus 1 modulo 11. Since 6 GCD of 6 comma 11 is equals to 1, therefore we can divide here by 6, and therefore we get x is congruent to minus 1 modulo 11, and that is equals to x is congruent to 10 modulo 11, since 10 is congruent to minus 1 modulo 11. Okay, so here 10 is congruent to minus 1 modulo 11, therefore we can write this minus 1 as congruent to 10, and thus we get the required solution. Okay, which is required solution of given equation. Okay, so here we have completed our examples. Now we see in next lecture some more example and the theorem. Okay, thank you everyone.